Welcome to this operational explainer. Today, we're diving deep into the strict, sequential protocols required for high-purity starch extraction. As industrial chemists, we know precision here isn't just an option, it's a mandate. So let's break down the exact chemical and mechanical parameters that dictate our yield.
Consider this metric for a moment. Our absolute baseline for success in this facility is an uncompromising 99.5% analytical starch purity. Anything less? Well, that's classified as a process failure. Achieving this level of purity isn't a matter of luck. It requires relentless chemical engineering and mechanical sorting. We literally have to strip away every single fraction of protein, fiber, and lipid until absolutely nothing but a pure starch matrix remains.
To hit that 99.5% purity, we'll walk through the process flow chronologically, starting with the sulfur steeping protocol, moving into mechanical germ separation, centrifugal density fractionation, hydroclone purity optimization, and finally, thermal dehydration and analytics.
Section 1. The Sulfur Steeping Protocol. Initiating biochemical disintegration.
The protocol kicks off by structurally compromising the raw flint maize kernel. We do this inside our multi-tank countercurrent steeping batteries, running precisely between 48 and 52 degrees Celsius. And let's be clear, we are not just soaking grain here. We are executing a microscopic attack. We actively target the hydrophobic Zein and glutenin proteins. By forcing disulfide bond reduction, we cause the rigid crystalline endosperm matrix to collapse entirely, which is literally the only way to liberate the starch granules locked inside.
Think about the chemical kinetics at play. The sodium bisulphite actively severs the cysteine linkages. The sulfurous acid reduces those bonds, and this chemical reaction is fundamentally non-negotiable for separating the starch from the protein network. Plus, this biochemical disintegration also alters the corn by freeing up bound nutrients like niacin. But here's the catch. Operating below a 0.1% sulfur dioxide concentration during this primary steep phase is an operational death sentence. If you let that concentration slip, you'll instantly breed a wild microbial colony that will literally consume your entire batch from the inside out. You have to maintain that strict 0.1 to 0.2% window to ensure you have the necessary sulfurous acid to attack that Zein matrix.
When you execute this chemical disintegration flawlessly, the softened corn kernel absorbs water until it swells to twice its dry volume. It will reach a precise target mass point of exactly 42% moisture, and as you might guess, this metric is absolutely non-negotiable.
Hitting that exact 42% threshold is what readies the matrix for the degerminating mills. It ensures the bond between the starch and protein is sufficiently weakened. This prevents premature mechanical failure and allows us to seamlessly isolate the starch later in the pipeline.
Section 2. Mechanical Germ Separation. Precision Attrition Milling.
Once chemically loosened, the slurry enters our first stage mechanical loop to isolate the high-value germ. Now, if you set the disc mill gaps too narrow, you get what we call shear over-intensification. This applies excessive physical shear that actually tears the fragile germ membranes. Doing so triggers a catastrophic release of free lipids directly onto your starch granules. This is an irreversible contamination, instantly disqualifying the product from our 99.5% purity classification. So our operational steps have to be strict. We route the softened kernels through precision clearance disc attrition mills. The goal here is gentle tearing, not pulverization. We rupture the pericarp just enough to release the intact germ body. This cleanly isolates the 12% total germ mass before we direct the slurry into liquid cyclones, where centripetal force just floats that buoyant, oil-rich germ right away from the heavier endosperm.
Section 3. Centrifugal density fractionation. Hydraulic mass balance.
After mechanical separation and multi-stage wedge wire screening to scrub out the fiber, we're left with a binary mill starch suspension. This has to be separated based on sheer physical density. We exploit the stark difference in specific gravity between the heavy starch granules, which sit at roughly 1.50, and the lighter gluten proteins, which hover around 1.10. We rely on continuous, high-speed nozzle centrifuges to execute this sorting based purely on these cold, hard density metrics.
This brings us to the most critical hydraulic parameter in the facility, 1.04. To execute the separation in the centrifuge, the specific gravity of the feed slurry must be adjusted to exactly 1.04. At this specific density, centrifugal force perfectly drives the heavy starch to the outer perimeter,
while displacing the lighter gluten to the center. Any deviation from 1.04 is totally unacceptable.
Nailing that 1.04 specific gravity prior to the centrifugal separators is an absolute requirement. If permitted wash water dilution drags this specific gravity below the 1.04 threshold, complete hydraulic collapse occurs inside the rotor. And the result? The lighter gluten proteins are immediately sucked into your pure high-velocity starch stream, utterly destroying your chemical specifications.
Section 4. Hydroclone Purity Optimization. Multi-stage separation.
Now, the primary underflow exiting the centrifuge is still going to contain trace levels of insoluble gluten. That necessitates a final, brutal physical washing phase. We route the concentrated starch into 14 successive stages of miniature 10mm ceramic hydroclones. We inject fresh, softened wash water in a strict countercurrent configuration, meaning it flows backward while the starch solids move forward. The intense G-force rotational velocities inside these tiny hydroclones aggressively strip away every remaining milligram of adhering protein, expelling it right out through the vortex finders.
But be warned, you have to maintain absolute header pressure here. A hydroclone pressure shock, which is just a sudden pressure drop across the system, will instantly break the internal fluid vortex. Your heavy starch solids will stall out and immediately remix with the rising protein-heavy overflow. That's a massive purity failure, requiring a complete system recirculation back to the raw surge tanks.
Section 5. Thermal dehydration and analytics. Stabilizing the end product.
With our starch milk analytically verified at that 99.5% purity mark, we have to immediately stabilize the batch, while simultaneously extracting maximum economic value from our side streams. Take that 12% corn germ mass we isolated earlier. We condition it at 90 degrees Celsius, run it through mechanical expellers, and then process the residual cake through rigorous countercurrent solvent extraction. Using industrial-grade hexane, we strip residual lipids down to less than 1%, maximizing our yield of premium, high smoke point salad oil.
But this side stream process carries immense risk. If your stripper, desolventizer toaster drops in temperature or lacks adequate steam injection, volatile hexane remains trapped in the spent germ meal. If that happens, you haven't just legally reclassified your animal feed product as hazardous waste, you've essentially built an active, catastrophic bomb in your storage silos.
Returning to the purified starch, dehydration must be exceptionally rapid to prevent microbial resurgence. At 0 seconds, continuous vacuum drum filters drop the slurry down to a 35% moisture cake. At 3 seconds, a pneumatic flash dryer hits that damp cake with a 160 degrees Celsius high-velocity airstream. By 6 seconds, the moisture plummets to a stable 12%, yielding a mathematically pure snow-white powder that's fully verified for industrial distribution. So, I'll leave you with this final, critical diagnostic question. Are you strictly holding your 0.1% sulfur window, and are you feeding your centrifuge at exactly 1.04 specific gravity? This entire wet milling protocol requires relentless discipline. It is a precise, uncompromising balance of chemical engineering and mechanical force. Monitor your pressure drops, trust the chemistry, and whatever you do, do not deviate from the data. That concludes this operational explainer. Maintain your parameters, and you'll guarantee that 99.5% purity target.